Marcel. So, talk with us. Oh.
Okay, so our chair is just in the chair. Say that we should start.
Yeah.
Because the speaker wants to speak.
Sorry, I thought you were the chair. Yeah, so welcome everyone for the second day. So we'll start with Fernando, then we're going to have Nadia the second talk. So yeah, please, Fernando.
Thank you, Rafael. Hi everyone, good to see you again. I want to review a little bit what we did last time, like for 10 minutes, and then we go to new things. And please ask more questions today as well. So yesterday, all the questions were really good, so please ask more. So the topic right of my lectures is quantum error correction, right? And today we'll get to the specifics of superconducting qubits, and then we'll be able to talk about the experimental progress on quantum error correction in that platform, right? So that's where we want to go. But I just want to revise quickly what we saw last time. So last time we saw that in quantum mechanics, there is two types of errors, right? There is bit flip, where 0 becomes a 1, 1 becomes a 0. But now, because there is superposition in quantum mechanics, there is also phase flip, where a plus becomes a minus, and a minus becomes a plus, right? So it's more complicated than classical information. There's only bit flip in classical information, but it's not like increasingly more complicated, as some people thought before, in early times. Then I show you a very popular quantum error correction code that we can interpret, if you want, as a quantum generalization of the repetition code, which is the most basic, right, classical error correction code. But whereas the repetition code is a good code to learn about error correction, but it's not a very practical one, and it's not really used in practice. The surface code is really, as far as we know today, maybe the best, or at least one of the best codes for building in the future a fault-tolerant quantum computer, an error-corrected quantum computer. Right, so we have a square lattice. If you remember the white circles, the data qubits, where one logical qubit lives delocalized among all of them. Because of quantum mechanics, we cannot measure directly the data qubits to see, right, if there was an error, otherwise we collapse them. Then we need some extra qubits. These are the ancillary qubits, the black circles. And then we use the ancillary qubits doing this kind of circuits, right, to measure what we call stabilizers on the data qubits. So these stabilizers, they are either four-body operators. In the surface code, they are Z, 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 green, and X, 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 yellow. And on the boundary, they become free-body. If you want to do closed boundary conditions, they're all four-body, and this is toric code. I show you. I mentioned that the qubits live in the common eigenspace of eigenvalue 1 of all these operators. Right? All these operators, they are product of Pauli matrices, so they have plus 1, minus 1 eigenvalues. They all commute, right? This is something that we also, I argued last time. So they have a common eigenvalue 1 eigenspace, and the qubit is there. The logical qubit is there. And I also show you that we can understand the structure of this logical qubit by looking at the structure of the logical Pauli matrices, right, on this logical qubit. And the Pauli matrices are very nice. They're just any kind of string of x's that connects, to upper end to lower end, and the same thing for z. But as I mentioned, they can twist, right? No problem. There's like many of them. The z will come here, go here, come back. So they're all the same, right? So it's kind of a degenerate code in that sense. Then I told you how we do error correction, right? So if you have an X error, these two stabilizers, they fire up, and you have an error. If you have a Z error, then the X stabilizers here will fire up, and there was an error. If you have two errors, then these two fire up, right? So you always get information about the endpoints of a string of errors, right? So that's what happens. And I also told you, that you cannot a bit slowly. That you cannot correct every error. If you have like a four-body error, but the same would be for a three-body error, this you cannot correct because you would get these two guys fire up, right, with -1 outcome, but you will not be able to tell if it was this or if it was this error instead, they have the same syndrome, the same outcome. And because if you combine them, you get a string that connects, right, the two endpoints, upper and lower. This becomes a logic error, right? If you think you have one, but you have the other one, if you make a mistake in the detection. So this is an uncorrectable error, and this makes sense, right? So this is a distance v code. You can correct that both errors of weight g over 2 minus 1. So that's the surface code. Now, it doesn't stop here. If you really want to use, okay, so then I have to tell you what happens in general, right? So in general, you have the following problem. You get a bunch of x and a bunch of z stabilizers, right? They get -1 after you measure them. So you have a situation like this, right? You have like your square legs, and suppose an x and z can be decoded separately, right? Because, you know, as I mentioned before, right, really x only detects z errors and z stabilizer only detects x errors. So the decoding problems completely independent. So just think this is a bunch of, you know, x stabilizers, for example, they got -1 eigenvalue, you got one here, one here, one here, one here, one here, one here. And we do know they are endpoints of strings of z errors, right? This we just learned before. But how do we know, if this string is here, or if this string is here, right, or if it's here? This we cannot get from this information, right? So we must guess. You know, there's like some guess that we have to do here now. And we want to do the guess, which gives the maximum likelihood of success, right? So there is a way to define what we call the ideal decoder. This is called maximum likelihood decoder, and it exactly solves the maximum likelihood problem, right? So you look at the probability of getting all possible strings of errors that have these endpoints, and then you see what is the one that has the highest probability of happening, and then you just assign, right, you do a matching, like here, according to this distribution. Okay, so you can do that, but that's kind of costly. Then there's a proxy for that. It's called minimum weight perfect matching. That's a very efficient algorithm that just allows you to basically, you know, given a graph of a bunch of vertices like here and edges, weighted edges, gives a match which minimizes the weight of the edges. So then the idea is that we just, you know, look at all here, for example, you know, pairs, and we do a weight to this edge, which depends on the error model, right? So for example, you know, to connect these two guys, the weight probably is larger to connect these two guys, right? Because you need like a higher string here, a longer string here, and it is more unlikely to happen, right? If you have independent errors, for example. And many other things related to, you know, measurement error and so on. And then you solve this, and then you get a matching, right? Once you have this matching, then you say, okay, I have an XX error here, right? I have an XX error here, I have an XX error here. I can undo this error, and then I correct the information, right? So that's how it works. Remember that the generated code is perfectly fine if, you know, the error was not this one, but it was like a string going like here, for example. That's fine, right? What is not okay is this kind of, you know, if you think that, you know, if you think there was the error, but actually the error was going here and going here, right? And then you get a logical error, right? But then the game is that when the distance grows, and the logical and the physical probability of error is not too bad, the probability that you know, doing this process, you get a logical error becomes smaller and smaller and smaller, right? And this property is what we say that the code has a threshold, in the sense that, you know, if the physical parameters are good enough, when we increase the distance of the code, the logical probability of error, which is exactly this probability that we induce a logical error during this matching process, becomes small, and we can show that it will be exponentially small, as I showed in the next slide, in the physical probability of error, where the exponent is like the distance of the code. Okay, so this is great, and this works, but as long as you can detect the syndromes perfectly, right? Because that is all about just the errors that were already there, right? When you start doing this decoding process. But that's not how we do in practice, right? Because everything has an error, as I mentioned before, right? So for example, when we are running, let me go back here. A bit slow. When we are running these circuits, right? We have to run these circuits to do, you know, to measure the syndromes. There might be an error here, right? Or there might be an error in the readouts. Or there might be, you know, X error in any of these locations, right? And then we have to handle this as Luckily, there is a way of handling that. Let me go back there where I was. And what you do is this is a plot from a recent experimental paper by Google on error correction that I will discuss in 20 minutes. But yeah, I like it because it's easy to see what you have to do. Right, so that's your initial states, okay? You have some initial state that you infer there. And then you start doing the circuit for error correction, right? So you apply, in their case, instead of CNOT, they do CZ gates, but they're equivalent up to a single qubit Hadamard gate, right? So they have to do a CZ, a Hadamard, another CZ, a Hadamard, another CZ, another Hadamard, right? So it's kind of, to measure one syndrome is a depth 4 circuit. You apply, in this case, 4 CZ gates and 4 Hadamard gates, or you can apply 4 CNOT gates, as we saw before, right? So this will be this process. And then you measure some qubits, and then you get some outcomes for your unsealed qubits. And when you get a 1, this means that there was like an error there. But now this shows that you can have kind of what's called a space-like pair, for example, when an error happens here and gets propagated by a 2-qubit gate, right? That happened before this, because that's the danger, right? So you can have an error in a qubit, but then you have a 2-qubit gate that appears after that. Then the error can spread, right? Now the error can touch 2 qubits, and then it can keep spreading. And the idea that you have to keep this under control. And that's why it's very good that it's a short depth surface that we have here for measuring the syndrome, right? So you do get this kind of what we call space-like pair, which is error that happens just because 2 qubits independently, got an error. There is time-like pair, which is this that I mentioned now, where you have a single qubit error, but then it gets propagated by 2 qubit gates into 2 qubit errors. And you can have combinations of it. So you think about the whole process now in 3 dimensions. So instead of a 2-dimensional problem, it becomes a 3-dimensional problem. But you can, in the same way, put some weights on these edges of this hypergraph, which just tells you, what is the probability of each type of error depending on the propagation and the probabilities that they happen physically. And then you create something like this, meshing graph, but it's a 3-dimensional one, like this, for example. And you run the same thing. You run minimum perfect mesh. It's a little bit complicated to do in practice, right? But many people do this by now, right? And there's many codes available online as well, like this combination of steamed and pi meshing that does this for you. So you can do that for very general error models. And once you do this, you can just numerically estimate the logical probability of error. Okay, and so that's how the procedure works. Any questions before I move on? Okay, so then what happens once you do that? Once you do that, we can start having this kind of plots, which we see a lot in papers on quantum error correction. So here on the y direction, we have logical x error rate, so it's the logical x probability of error, right? So it's the probability that you have a bit flip on the logical qubits. We can have the same thing for z errors, usually they're symmetric. And here we have the physical error probability. So this depends a lot on the error model, right? And I'll discuss a little bit error model more for transforms later. For simplicity, we assume there's a single parameter, p, for which each component of the circuit errors with this probability. So kind of a depolarized error model, if you want. So with probability 1 minus p, your gate is correct. With probability p, it's completely depolarized. It becomes the maximum mixed state. The same thing is true for the measurement, the same thing is true for preparation of the state, the same thing is true for 1 qubit and 2 qubit gates, right? In practice, this will not be the case, right? The speeds won't be the same, right? And the polarizing noise is not always the right one. But just to have a nice plot with just 1 p, we can start from that, right? Then if you do that, you start seeing some interesting behavior, right? So the colors, sorry, you cannot see so well, but I'll try to help. So this is the distance of the code. So we have a plot for how the logical x error rate behaves as a function of the physical probability of error. So of course, when the physical error probability decreases, the logical error probability decreases as well, right? That makes sense. The monotonic in sense. And also when the distance grows, right? So distance starts at 3, then 5, 7, 9, 11, 13. It's always odd because even doesn't make sense, right? Because I just explained to you that a code of distance t can correct z over 2 minus 1, right? So you see that doesn't pay off to stop at even. You always go to what for maximum benefits. And then distance 3 is the first one. You have this line here, okay? Then distance 5, the second is already better. Look, it's like a sharper, right? decrease of logical probabilities of error. Then, distance 7 is this one, and so on. It's like getting this sharper and sharper thing, right? Another is an interesting thing here, which is, below this crossing point, the logical probability of error decreases with the distance of the code, right? So distance 3 is the worst, then distance 5, then distance 7, distance 9, and so on. And that makes sense. Right? That's what you like to have, right? You like that once you invest more qubits in your encoding, in your error correction code, you get better performance of the logical qubit, right? So that's nice. But you see above here, that's not the case. It's like a mess, it gets worse, right? You increase the distance and it gets worse. And there's a crossing point, and these crossing points, you see it's almost like a phase transition, right? And in a sense, for this simplify what it is a phase transition, you can map to some. You can map this point exactly to some stat-mech problem and to the firm of phase transition there. I won't cover that, but in the sense that it's really related to phase transition. And this is a number, right? This defines physical error probability here. I'll tell you what it is for the surface code next, but it's around, like you can see from this plot, around like 1%. And this is called the threshold of the code. And every kind of family of codes in large indices have a threshold. Well, if it's a good code, it should have a threshold. And this threshold is a very important parameter because it tells you that you need your physical components, right? Your gates, your measurement, and so on, to be at least, the error probabilities have to be smaller than the threshold error probability. Because otherwise, there is no point in enlarging the code, you just get worse and worse, right? So error correction works, but not at every physical probability of error, every physical error rate. Your components have to have a good enough physical error rate for it to work, right? Which makes sense, right? Because you see, there was very complicated circuits, and I didn't really prove to you, but I handwave said that right, the propagation is not too bad, and then the measure stabilizes, the error doesn't spread too much, and then it still gets a benefit. That is true, but only if the physical probability of error is small enough. Using these kind of simulations, right, that many people do, we can get this kind of plots, which is very interesting to understand. So this is the error rate of your physical components here, from 10% up to 10 to the minus 4. And okay, I didn't put here, but there's like a target logical probability of error. In this plot, I think it's something like, we want to get a logical probability of error like 10 to the minus 8, 10 to the minus 9, something like this. Right? So much more than what we have today. And then we ask, okay, given a physical error rate, how much qubits we need in the code, for example, to achieve it, right? What is the qubit overhead? And then we get a curve, right? We get a curve. And this curve, always kind of saturates at some point. This is the error correction threshold, right? So you'll never be able, the overhead really becomes infinity, right? If you're above the threshold, error correction doesn't work. If you're too close to the threshold, the overheads usually are terrible, right? Because, if you're very close to the threshold, you increase the distance, and you only get a tiny improvement, right? So, it improves, but very, very, very little, right? So really, you like to be far away from the threshold, sufficiently far away from the threshold, and then things become nice. Can we get a formula out of this, right? It turns out that we can, and it makes sense. That's an empirical formula, of course, right? So there's no, it's not, there's no theorem like proving this for surface code, but it's an empirical formula and it makes sense. Again, it's this depolarizing error model, which is a very simplified one, but still, right, gives some flavor. So what we can get is that the logical probability of error as a function of the physical probability of error, P physical, or P that we call last time, and the distance of the codes. There's a prefactor, 0.1, doesn't matter too much. Then there's the physical probability of error divided by the thresholds. The threshold for the surface code in this error model is like 0.7%. It depends on your assumption. Sometimes you get different results, but that's usually is close to the truth. So it's 0.7%, right? So this tells you basically, right, how would you have to be in the lab, right? So if you're doing your experiment, you're getting 2 qubit gates, which are like 2%, 3%. Forget about it, right? You should not be attempting to do error correction. You should be trying to improve your gates before you do error correction. Now, if you're in your lab and you have 0.7%, right, like average 2 qubit error rates, maybe you should not try this as well, right? Because you see no improvement, right? And if you have 0.006, so 0.6%, you might get improvement, but it's very small, right? So you have to be careful. So you like to be 0.1%, right? Then you get a nice number, right? Because then you get like, basically 1/7 here. And then that's the very interesting thing of error correction, and that's why, we think that we can reach this 9 orders of magnitude, right, that we want to reach, as I mentioned last time. Once you get a good base here, which requires a good physical probability of error, it's exponentially the distance, right? The decrease of the logical probability of error is exponentially the distance. So this is, right, a very fast decrease. So here's some examples, just putting some numbers to this formula. If the physical probability of error is 0.5%, and this is kind of state of the art, as I'll mention soon, then you can get a decrease, but it's kind of minor, right? So it's like it's at 1.2%, it's even worse, right? So first you don't even get a gain, then at distance 9 you get some improvement. Oh, sorry, this will be distance 7, it's at 5. And then distance 9 falls to -4, which is already good, but very far away from where we want to be, right? If it's 0.1%, it's already bad, right? So, because as I mentioned, you have this like 1/7 here. And then, of course, you have to see, okay, how many qubits I need to have these logical qubits with this distance, right? That's the formula. It's 2d squared minus c, if you just count how many oscillas and data qubits you have. And then you see here, right, for distance 5 is 45, for distance 7 is 153, for distance 9 is 435, right? So, okay, it is what it is. As I mentioned, if you want something in 2 dimensions, okay, now I can tell you why the surface code we think is a good code. So first is in 2 dimensions, and only local connections. That's very helpful experimentally in many platforms. But second, it has a very high threshold. So this threshold of 0.7%. If the repetition code is a classical code, it has a threshold as well. It's 3%, right? So of course, surface code is worse because you have to correct X and Z errors, more complicated. But it still has a good threshold if you compare to any other codes that we know today. The thresholds will be worse, right? There's some failure codes for like color codes is like 0.1%, right? There's called LDPC codes. They are newer codes and they are nice, but then it's even like sometimes 10 to the -4, 2 times 10 to the -4. So the fact that the surface code has a large threshold that is in 2 dimensions is the reason why right now that's the main contender for error correction for how to error correct quantum computers. Moving on. Any question? Okay. All right. So this is a quantum memory, right? Which is great, but we like to do quantum computation, right? And to do quantum computation, I'll have to tell you now how to use this memory, logical qubits, right? So, put them together and do logical gates on them, right? And in the end, do a universal set of logical gates on them, right? And I will just quickly mention how to do that. I won't spend a lot of time, but I want to give you a flavor, right? Just for you to have a complete picture. So this is just some gates I use. Of course, the X gate, that's the matrix form. You guys all know, right? There's the Z gates, with just a -1 on 1. There's the Hadamard gate, right, which changes computational basis to rotated basis. They're all here already. We will need some new gates now. Okay, so also the CX gate or C0 gate, you also saw that, right? It's a NOT gate on the second qubit. If the first qubit is on the 1 state, that's the matrix form of it. You can have swap, right? We just change it to qubits. And there's a new gate that I have to introduce you. This is called a C gate. It's similar to Z gates, but you take the cubic roots of the C gates, and then you get the T gate, right? So you get this phase of e to the I pi over 4. Okay, it just puts this particular phase on the 1 state and does not into the 0 state. Why I introduce these T gates? Because there's a nice result, which is that Hadamard, this one, C0, this one, both very soft, right? And they appear when you want to mesh the stabilizers in error correction. And the T gates, they form a universal set of gates. So in the sense, you can write any quantum algorithm that you can think of in terms of circuits of these 3 gates, and you don't lose much. Like the overhead is very small. Let's remember, it's a little bit more than square of the logarithm of the error that you want in the conversion, right? So it's very, very efficient. It's called Solovay-type theorem, and this is a universal set, so you can just use that. Okay, there's many other universal sets, right? But this will be very useful because they work well with the surface code basically. So I will have to tell you how to do logical Hadamard operation, right? Logical CNOT gates and logical T gates on logical qubits on the surface codes, and then you understand how to do universal quantum computation, right? So that's what I will do next. Any questions? Okay. So let's start with Hadamard. So logical Hadamard is the simplest to implement, and it's implemented called transversely. So a transversal gate is a useful concept in fault tolerance, and it's a gate for which there is the physical implementation of the gate consists of applying single qubit gates or 2-bit gates if it's a 2-qubit gates between pairs. Okay, so for single qubit gates you carry codes, you apply a single qubit gate to every qubit in your codes, and this is the realization of the logical gates that you want to implement. In the Hadamard, it's even easier. If you just take all your data qubits and you apply a Hadamard gates to each one of them, I claim that you implement the logical Hadamard gates. Okay, so that's the claim. After rotation of the lattice, which you have to compensate in other ways. And why that's the case? Because we have this relation, So if you conjugate the Pauli Z matrix by Hadamard, you get the X matrix. And if you conjugate the Pauli X matrix by Hadamard, you get the Z matrix, right? So that's an easy exercise you can check. And now suppose we apply that to the surface code, right? We apply to each of these stabilizers, right? So what this does, it maps Z stabilizers to X stabilizers, and it maps X stabilizers to Z stabilizers, right? But now suppose you take this guy and you just change, right, the colors. Whenever you have green, you put yellow. Whenever you have yellow, you put green. You get this, right? Which again is a surface code, right? But a surface code, kind of rotated where X is Z, right, and Z is X, right? Which is exactly the logical Hadamard, right? So that's the argument. It's very simple in this case, and then it's very nice, right? Because it's really it's very fault tolerant, right? In the sense that errors don't propagate, right? If you just apply a bunch of physical Hadamard gates and there's an error, after the application is still just one error, and the error correction protocol will correct, right? So how we do that in practice? Just to make a question last time. You apply many rounds of syndrome here, right? So you apply usually D rounds. You have a distance D codes. After you apply these D rounds, in depth 1, you apply Hadamard on all data qubits. Of course, this might introduce some errors. And then after that, you apply again D rounds of error correction, right? And the claim is that if you do this, you get a logical probability of error for the implementation of the Hadamard gates, which is roughly as good as the logical probability of error that we had for memory before. Right? So that's how you do this logical single qubit Hadamard gates. Clear? Okay. How do you do CNOT? CNOT is a little bit more complicated, and I'll just roughly mention. I want to give you 2 arguments. Basically, we would like to do. Remember, we want all our qubits in a square lattice, right? And they have patches of the square lattice, and this will be where logical qubits live, right? On kind of like a D-dimension, distance D surface code, right? So imagine they have a surface code here with a logical qubit, another surface code here with a logical qubit, another one here, and we like to do CNOT gates. So in this setting, we don't really have, and we can only kind of do this local operations, right, on neighbors here. So we don't really have a good way of doing a CNOT gate directly between 2 logical qubits, but we do have a way of doing one if we are allowed to introduce an extra logical qubit as an ancillary qubit, which is this guy here. And the circuit that we use is the following. It's kind of a little bit complicated, but it's it what works. You can write the CNOT gates in a measurement-based way, which is a little bit related for like gate teleportation, where you prepare a CNOT in the plus states, and you have the the control of your CNOT gate and the target of the CNOT gate as before. And then first you make a measurement of the stabilizer ZZ on these first 2 qubits, right? So this is just for context, right? In the surface code, we are measuring MZZZZ, right? The 4-body one. Here is just a 2-body version of it, right? Which appears, for example, in the replication code, right? So you just measure this, right? This has a +1 and ±, eigenspace. We measure this. We project this guy, right, into a smaller subspace. We get some outcome A. right, -1 to the power of A. So A is either 0 or 1, depending if you get eigenvalue -1 or 1. Then we do the same thing, but now with XX, Pauli XX, on these two lower qubits. You get, again, an outcome. Then condition on the outcomes, A and B that you got, you apply some correction operations. You apply X, right, A plus C. So either you apply X or you apply the identity, depending on the carries of A plus C. You apply Z to the power of B, right? And here you just measure this oscillor, so it doesn't exist anymore. And depending on the outcome of the measurement, you just put some, phase, which, right, is not so relevant, but it's a global phase. So that's a complicated circuit, but that's it's a good exercise in quantum mechanics, right, and quantum information, just to prove this identity. I think you should try to do it. If you try and cannot do it, I can help you, but try to do it in the next, maybe at some point today. And why that's helpful? Because this is, you can check in this paper, and it's a nice argument, but there's operations that you can do on patches of surface code, which exactly implements these two measurements. Okay, this one and this one. And these operations are the following. The first one, you get two surface codes, you have some, connecting qubits, and then you just treat this as a big surface code. It's called like a merge of two surface code patches, just by measuring the stabilizers here, which you were already measuring, but also stabilize at the boundary that you're not measuring before. And then if you measure many times, the claim is that you have implemented, sorry, in this case, MXX. No, sorry, I think it's MZZ. MZZ right in these two patches on the surface code. Then, I'm sorry, so it depends on the boundary. So if you connect this in the X boundary, you measure XX. If you connect in the Z boundary, you measure ZZ. That's how you do, right? And that's why it's connected this way. That's great. So this you can do. So this kind of merging where this becomes a bigger surface code and then this becomes a bigger surface code, right? In the end, you just have like a very big surface code here of the three of them. This implements this MZZ, then this MXX measurements. Now we have to implement this MC, right? And what you do with this MC is also similar. It's called splitting of the surface code. Basically, now you measure this, this spin qubits in the computational basis. Okay, so you just measure them in your computational basis, and if you do that, you merge the surface code, you break the surface code into two independent ones, and then exactly implement this logical MC that you want. So this is, I'll ask you to check this for details why that's the case, but it is the case. And that's how you want to do inference, right? So that's not so bad, right? Because, if you can do the memory experiments for each one of them, CNOT, and this is called lattice surgery, right? It's called lattice surgery because they're basically these surgeries on lattice, where we're enlarging them once we merge them, and we are splitting them once we want to apply this measurement on Z. So we do this all kind of like lattice surgery, which doesn't physically, it just really measures stabilizers, right, in the particular order, and this does the CNOT for you. So I show you how to do Hadamard, how to do CNOTs, but how to do C-gates, right? And that's where, unfortunately, it's a little bit more complicated. Again, I just want to give you a flavor again. It turns out that C-gates, you cannot do just by using the memory and doing stabilizer measurement on the memory and single qubit gates as was the case for CNOT and Hadamard. You need a different process. And the way to understand how you do this process is assume that you have, that's the reason for the name, a magic state. A state that was given to you by magic at first, which is this C state. So this C state is a state of a single qubit. I should have written it. It's just 0 plus e to the I pi over 4 1, okay? Which is exactly the state that you get if you apply the C gate, the 0 plus 1 state. Suppose you have these states. Then there's this very simple circuit. I think it goes back to paper Goldman and Schwab from the book a long time ago, which is called single qubit teleportation or gate teleportation. If you're given this resource space and in this very simple circuit, you're applying CNOTs, you measure the target qubits and then condition on the results. Either you do nothing or you apply a phase gates, which is just the square root of the Z gates and the X gates. And by the way, the S gate you can also implement transversely on the surface code, I didn't mention. Then this process allows you to apply the gates to the state side, right? So the idea here is that you're in a situation where you can apply a CNOTs, you can apply a S gates, you can apply a X gates, you can measure, but you do not know how to apply this thing at C gates. If someone gives you this magic state C, this protocol allows you to implement the gate C, right? So that's disclaimer of single qubit teleportation. And why that's helpful here? Well, because C0 we just saw how to do on the logical level, right? Measurement we can do the logical level, we just measure every qubit in the surface code. X gate we can do the logical level. X is also transversal, right? If you apply X everywhere, you do get a logical X. S I didn't tell you, but it's also transversal, right? So you can also do it transversally. So we know how to do this in an easy way, transversally, right on the surface code. So if I'm giving this state C, not as a single qubit state, but encoded in the surface code, then you can implement logical C gate, and you can do universal computation. Now the problem is that how to get these magic states, right? So you won't be given them right by magic. So you have to prepare them yourself, and that's what is called magic state distillation, which is complicated and it used to be very costly, but because many optimizations is not so costly anymore, and it's not what determines the overhead in practice. But the idea is just to get another error correction code, in this case like a 51 code, and you get codes that has transversal C gates on the code. And then you kind of think that the circuit is such that if you start with, there's a circuit identity here, right? So you start with plus and zeros. You apply this kind of complicated sequence of C0 gates. You apply the conjugate of the C gates. You measure everything X. You post-select on everything being 0, and then the claim is that you get a T state as an output. This is an identity that you can check. Then how you do that as a magic state kind of distillation? The idea is that you start from some physical C states that you can prepare in the lab, but they have noise, of course. Then you run this protocol. Now you just use this gate teleportation to implement this kind of conjugated C right here. You measure, you post-select on 0. And now what you can prove is that in the end you get one copy of a magic state, but with better fidelity. This kind of improves the fidelity of the gate to the process. And then you repeat this many times. And when you repeat sufficiently many times, you get a very good C gates and gates. So that's what you have to do, right? Don't worry about the details of the circuit. I won't have time to tell you how it works. But it's kind of is a little bit more complicated part of the protocol, right? Which unfortunately is necessary for universal quantum computation. Right? There is no way to do just everything transversely. This is also known. There is a no-go. It's kind of there is no way to do universal quantum computation transversely on any code. Well, not any code, but any kind of stabilizer code, pretty much. So you do need this complicated step, unfortunately. But with that, you are done, right? So that's how a quantum computer maybe will look like one day. Where you have your logical qubits. They are here. They should be square ends. Here is rectangular because we can generalize this, as I will show you later. But anyway, you have your logical qubits here. So this is like a your storage of the quantum computer. Then you can, and then here on the side you have this magic state distillation factories, right? On the side you run this protocol I told you, and you produce a lot of magic states there, right? It's like then you need like some space to move things around. So these are all like working space where just by logical swaps you kind of move the magic states around. You can implement the C gates when you want. You can move what is on Scylla, what is data qubits to implement logical CNOTs and so on. Yes.
So back to the T magic states.
Yeah.
So in the end you get really a qubit or a logical state, and then you have a concatenation of.
You do magic state distillation not at the physical level, at the logical level.
But then all the gates that you apply afterwards will have these overheads of that you are applying it on an error corrected state, so like on a logical qubit.
Right, good question. Yeah, well asked, right? So actually, this is done at the logical level, right? So whenever you have these gates, this is a bunch of logical CNOTs that you do, right? And this is really a logical C gate, which you can do by having a magic state and this, right? Logical operations as well. So in the end, you get a better logical C states, right? So this is done on the encoded level. This circuit. But it's okay, right? But the circuit, apart from this, C gates, which you can do like that, they all involve just the operation that we know how to do, right? Transversal, right?
Yeah.
Before you said that to get a sufficiently good error, I think you said with a good physical error rate would be something like 500 and something real qubits. But there is also some overhead from these gates that you need to implement and yes. Magic state distillation. Is this significant as well, or was it already included in that overhead before?
Yeah, great question. It was not included, and it is very significant. So the range is worse than what I said before, unfortunately. And I'll tell you actually right now what it is. For 2 examples, right? This really depends then on the algorithm that you want to run, right? Because it depends on the gate set, how many CNOT gates you want to implement, how many T gates you need, and so on, right? But so again, right? So that's again how it works, right? You have the logical qubits, you have some working space that you can move things around, and you have the magic state factoring, right? So that's one potential way of building a quantum computer in a 2-dimensional lattice using surface code, right? Going back to the question, right? It was a very good question. Okay, so putting everything together, right? What is the overhead that you get? And that really depends on the quantum algorithm that you want to run, right? Because it depends crucially, of course, on how many qubits you need, logical qubits you need, but also crucially how many T gates you need to know the size of the vectors, and even details about the sequence of the gates, because it tells you how much space you need for routing, right? It's kind of extra space that you have to put. So there's a lot of work in this direction. So the state of the art still today for factoring a 2048 digit number. Remember, the target was 6,000. What you need at the logical level is 6,200 logical qubits and 10 to the minus 2 error rates that I mentioned before, right? That's just what you get once you put short algorithm and optimize as much as we know today. If you translate into everything that I said, you need 20 million qubits. If your physical error rate is 10 to the minus 3, if it's 10 to the minus 4, maybe I think it's like a million qubits, right? I forget, but it's something like that. So lots, right? A lot of things. So and the overhead, right? Indeed, is much larger than this 500, right? If you just think if you divide 20 million by it's really more. But so another example, if you want to simulate the 8x8 hover model, which some people think that is already out of reach for classical methods. You will need 132 logical qubits because it's fermion, so you have to double, right? So it's 64 times 2. And because of kind of the circuit depth that we estimate that we need to compute, some good approximation of the ground state energy, you need 10 to the minus 8 error rates. If you convert, this is like 320,000 qubits at 10 to the minus 3 error rates, right? So, and that's kind of from applications that we might want to run on the quantum computer one day. That's the one that needs the least qubits as far as we know. So it's still a lot of qubits, right? So error correction in principle works. That's great. There is some early demonstration progress that I'll mention soon. But really, if you want to, really put it to use and build a technology, it's a long time away, right? And it's extremely challenging to do this large number of qubits. And this error rates, we are kind of close to it, but we're not there yet, right? And because this is so bad overhead, we like to be much better than that maybe one day, right? And that's something that I'll discuss more in the next slide.
Can you maybe comment a bit on runtime? Like all these clock cycles produce overheads for elementary operations.
Yes, so runtime, that's a good question. So runtime, and that's one reason why I like superconducting qubits, even though it's not great, but it's at least possible to do something. The error correction, right, there is a slowdown in the clock cycle, right? So error correction, imagine, if you want to do a logical operation, for example, I can go back here, like you want to inject a T-gate, a logical T-gate, then what do you have to do? You have to prepare these guys, you can prepare offline, so that's okay. You have to apply one logical CNOT, you have to apply a logical measurement, and condition on that, you have some feedback, and you apply this logical S and X, right? Each one of these logical gates, of these ones, you have to do a round of error correction before and after them, right? That's how we show that, that's how we keep errors under control. And a round of error correction really means D rounds of measuring stabilizers, right? So this grows to the distance of the code. If you want to get to very small error rates, like those, we need distance, and have 10 to the minus 3. Usually we need distance around in the 20s, I think. So it's like a circuit, maybe it was 1, 2. you have to measure for each logical operation that you do, each logical seed, you have to measure maybe around hundreds, right, stabilizer measurements, right? So the stabilizer measurements each takes in superconducting qubit, for example, around microseconds. So it's like already like 100 microseconds. If you go to ion traps, it's like a second. So it's bad because once you look at these very complex algorithms, if you want a factor, for example, this paper also optimized time, and they found that it would take a few hours to factor this number. Which is a lot, but it's right, it's reasonable. But now if you have something which is 100 times lower, right, then it's not so reasonable anymore, right? It takes like many days, right? Or maybe even weeks. So a logical clock cycle is definitely a bottleneck right now, and I think really, and this is for sure that has a huge speed up, right? If you have a problem with a smaller speed up, then sometimes error correction just unfortunately destroys the speed up. Right? So getting faster gates, faster protocol, faster error correction tools in schemes, that's a very important question. Any more questions?
So, at first, yesterday you were talking about the very different implementations of quantum computation.
Yes.
And at first it seemed like these codes were, in a sense, agnostic to the type of qubits that you implemented, but now it seems, after you said this, that there is difference. The fact, for example, that you need the cost, the number of measurements scaled with the size, it seems like it's more geared towards the superconducting qubits that you work with. Would you say that's a fair assessment?
I mean, that's my personal assessment. That's why I work with superconducting qubits. But if you talk to people on ions and Rydberg atoms, they have good points too, and their point is that, it's slow right now, but we think there is ways of making fast in the future. And they do have some credible path ahead. It's not easy, but it's not easy for anyone, right? So the technology is also, right, it's not set in stone what is the gate time, what is the measurement time, right? Everything is evolving, and they hope to make them faster. But it's definitely a bottleneck for the realization of today, right? Whereas superconducting qubits, it's extremely hard to do 20 billion qubits, and I'll discuss a little bit. No one knows how to do that really completely, but there's also credible path. But even if you just keep today the performance in terms of gate time and measurement time, would already lead to something that is possible, right? And that is interesting. Whereas for ions, you really have to make them fast. Photonics is already fast enough, and sometimes can be faster than superconducting qubits, which is exciting. The problem of photonics is just the overheads are really, really huge, because there's so much loss. But that's something that they think they can just figure out just talking to foundries and with CMOS technology and so on. So they also, each one has their own story, and that's great, right? And it's such early days for everyone that, honestly, I think none of them will be the ultimate way to build a quantum computer, right? Something better will come along. That's what I hope. But yeah, we'll have to see and wait what happens. Any other question? Yes.
Hello. In the implementation of quantum gates, you can have some errors, right? This is because this scale of how much you need to, for example, from 600 to 20 million qubits, you need much more quantum gates to reach between the data and see the qubits, right? This quantum gates between for to have the Silas gate can increase here. So
I don't know if I understood. Are you asking? You say, okay, you have to apply a lot of gates, right, for short, right, logical gates. So you need a very small logical probability of error, right? That's cool, right? You need those very small logical probability of error. And for achieving that, you need a very, very large distance for the surface code, right?
yes, so to correct the error, you need to implement more quantum gates, right? And this cannot increase the.
Oh, you mean if the errors, the gates increase?
And
No, right. So this is exactly from the threshold, right, that I mentioned before. So you imagine you have your, suppose we fix the physical error rate to be 10 to the minus 3, so 0.1%, right, so that's fixed. And now you have your surface code of distance, whatever, like 11, right? And then you have all, you keep measuring stabilizers all the time. And then you can do a simulation, and because it's below the threshold, this will give a logical probability of error, right, that we can compute. So now you're enlarged to 13, right? And then you're right, so you have more qubits, and you're running more gates, right? But kind of, the depth is the same, and that's kind of what's important, right? The depth is still the same with the circuit, so they don't spread too much, right? They still spread kind of the same way. And now because you have a larger distance, you can correct a large number of errors. And then there is a payoff. There is a gain, right? So the logical probability of error doesn't decrease, and keep decreasing. But that's only the case if you're below the threshold, right? So really, it's like a base is below the threshold is what I said, which is very nice. Above the threshold is what you say, right? You increase the distance, there's more errors, doesn't help you, it just gets worse, right? So this is really, it doesn't have to be this way, right? But it is this way, and you can actually understand that it's this way, at least in some idealized setting, really mapping this to a statistical mechanical model of classical schemes and mapping the error correcting properties to phase transition from a phase transition of this model. So then you really see that there is kind of a localized phase, and this localized phase is where error correction works because everything kind of doesn't spread too much. And there's a delocalized phase, which is when error correction doesn't work and then error just spreads too quickly and you cannot correct them. Yes, there's.
Good morning. Earlier you said that when you are implementing the ancilla qubits basis, you use diagonal basis. How is the choice of this basis for ancilla qubits? I wonder if it depends on the state you're measuring, but how does it go?
So you mean the rotator base? Okay, so the diagonal base, which is the computational base, is always 0 and 1, right?
Yes.
Then sometimes we also use the rotator base or the Hadamard basis, for which is and the base then is 0 plus 1 and 0 minus 1.
But it will depend on the logical gates you applied in your circuit to use the error correction, or not?
Sorry, ask me. I don't know if it depends on.
Depends on the phase gates you are using it, or no? If you rotate the bases or not.
Yeah, well, so, are you talking about when you measure the stabilizers or something else?
To do the error correction.
So to measure the stabilizers?
Yes.
Yeah, so indeed. So if you want to measure, let me go back to this stuff. I'll show you. It's easy. Right. So, right, here's the circuit. Right, it's unfortunately, and I'm sorry. So this is ground being 0 state, right? It's just like
right.
Once you go to so physics, ground would be 0, E would it's excited would be 1, right?
All right.
So if you want to measure Z, the Z stabilizes. Indeed, you prepare the ancilla in the computational basis, right?
Right.
If you want to measure X, then you prepare the rotator basis, which is the computational basis, where you apply Hadamard, right?
Right.
And you also measure the rotator basis, right? Oh, sorry, you measure then the computational basis. The rotator basis, because you apply Hadamard before, right? So to measure Z, everything is computational basis, right? Which makes sense because Z is diagonal to the computational basis.
Yes.
And to measure X, everything is the rotator basis, which makes sense because X is diagonal in the rotator basis, right? In the plus minus.
So it won't depend on the set of phase gates. Just in what you want to measure.
It depends on exactly if you want to measure a Z stabilizer or X stabilizer.
Right. Thank you.
Any other question? Yes.
About a month or so ago, there was this announcement of an alleged room temperatures, ambient pressure, superconducting material.
Right.
Would that have any implications for quantum superconducting hardware?
I mean, possibly. I'm not expert in superconductivity first, right? But and I'll tell you very little about that, but I'll tell you right now. So we will talk about superconductivity just starting out. For them, it's very important that you have low resistance there, right? Because resistance is basically loss, so you want to minimize resistance. So you want your material that you build the qubits ought to be superconducting. It's very important. That's why the name, right? So this temperature, the critical temperature of the superconductor they use sets upper bound on the cooling that you need to do, right? So you have to be below that. But usually you have to be much, much below that because you want to avoid all the sorts of error that we have that I'll mention, right? So the critical temperature is important, but it's not the only thing. Now if you have a higher temperature superconductor, in principle, you need less cooling. That would be great because you need a lot of cooling right now, as I mentioned. But it really depends on all the properties of the superconductor as well. It's not just the critical temperature, right? So that's the part that people that know better will have to see. But I read some bad news about, unfortunately, this high temperature superconductor today, right? So people at University of Peking, I think, Peking University, and apparently a very serious group, because there are many people trying, but these people apparently are very credible. That's where I read. They did very similar sample to the Korean, and they found just a ferromagnetic phase. And there is some easier explanation for the levitating stuff. So the latest news is not so good, but who knows, right? That's a good question. Yeah, also. I wanted the same, and I asked some people, but I got the answer that I gave you, basically.
Okay, thank you.
Yes, maybe this way.
What do you like? The reason why I think it's very interesting about like if room temperature superconductor would be very important or not is that because I think it's a cloud computing kind of model for the possible quantum computer. So would it actually matter or not, like this?
Well, it's what I said, right? So right now we need to pull superconducting qubits to 20 to 15 millikelvin. That's extremely low temperature, right? You need very expensive fridges for doing that, and you need a lot of cooling power. And once you want to scale up to million qubits, you need a large number of fridges, so the situation is not great in that respect. If you had a way of building superconducting qubits that could operate at room temperature, that would be game changer, right? That would be great. You don't need cooling. But just having a high temperature superconductor is kind of it's a necessary condition for doing that, but it's not a sufficient condition, right? So you need more properties of it. But definitely will be a great step in the direction of having room temperature superconducting qubits, which is something that there is no hope as today. All right. So what I want to do next, which I think I have like 15 minutes, maybe not, right?
15 years.
Yeah. So I want to start now, and I'll continue in the afternoon. So I thought I went less lecture here, so I'm running 1 hour late, but that's good. It means we're going the right pace. So I want to tell you the basics of superconducting qubits, finally. Then I want to mention some state-of-the-art experimental quantum error correction with surface code using the state-of-the-art superconducting qubit, which is called Transmon. But then, as I already argued, right, and I will argue again, that's a possible path for fault tolerance, and maybe that's the best, we don't know for sure. But it's just very prohibitive, the overheads, right? So this is a motivation for a different type of research that many people do. We also do internally at Amazon, that's why I want to talk about some work that I'm doing really right now, which is how to get potentially more hardware efficient quantum error correction using superconducting qubits. And there's two ideas. One is using dissipative gaps, which we're doing some experiments on, and doing a dual rail Transmon qubit, which we are also doing experiments on. And I would like to mention a little bit about this, right? And then, this will give you options if you want to use superconducting qubits to build a quantum computer. What's the best one? We don't know yet. Even we have worked on that for a few years, at least for less, but also for more than a year. It's very hard to compare the schemes, and this is what I want to also point out to, which is I think it will be a long time, as we have many platforms, even with these superconducting qubits, I think it will be many years until it really emerges as this is the way, this is the right way of building it. But there's a lot of exploration that has to be done, and the trade-offs, they are very intricate and complicated between them. So it's very interesting and fertile ground for research, but it's not kind of this, this race, right, view that we hear in the news about quantum computing and so on doesn't really make a lot of sense, right? It's really everyone aims to do it. All right, so superconducting qubits. let me just give you a general description that I will dive deeper. So we start from, suppose you have an electrical circuit that you learn in school, right? We have an inductor and we have a capacitor, and then we have a current going through, and this current, of course, right, will have, so this is like is a first order differential equation, right? Involving a second derivative, right? And the position kind of like a pendulum, right? The currents. So it will be like a sine and cosine behavior, right, of the currents. This we all know. It turns out that we can create artificial atoms in the sense of like mimic the spectrum of atoms. If we create really on the chip, right, we just use like lithography and we build on, for example, silicon substrate, we build some aluminum kind of circuit there, LC circuits, and we cool at very low temperatures so that we get some quantized electric circuit there. And then we get a harmonic oscillator, right? Because that's the quantization of a circuit like this. But now we put a different inductor, we put a non-linear inductor, and this we use a just junction for that. And then we get a non-linear harmonic oscillator, and this we use as a qubit. So if you do that, we will get energy. We get like levels, right? And they have energies, and the spacing between them will be like not the same; they'll be different, right? And then you can use the first two as a qubits, or any two as a qubit if you want. But usually we use the first two together. So what is this nonlinear element? And I'll deal more details in the next slide. It's just a just conjunction. It's just you take two superconducting islands. You put an insulator, usually like aluminum. That's aluminum usually is used. These days people are going to tantalum, which is better. Think about aluminum, and you put some aluminum oxides in the middle. That's like an insulator. And then, Joseph, right, got a Nobel Prize for showing that there can be tunneling of Cooper pairs, right? So this becomes basically a nonlinear inductor, right? So that's how we describe this. Where the inductance of this object depends on the currents that is passing through, using kind of also a periodic behavior, like a sine. So why we like to use these artificial atoms for quantum computing? Because they have some advantages. So first, they can be manufactured using microfabrication techniques, right? So not so dissimilar from how our computers are fabricated today in foundries, like CMOS technology. There is a difference, which is an important difference. We do need superconducting elements there, right? And these foundries are not used to that, so that's why right now we cannot outsource to a foundry to build a chip of superconducting qubits for us. But it's possible that they improve the process in the future for being able to work with superconducting elements, and then they could do it. So that's nice. They have very fast gates. I'll tell you what is the time, but it's on the nanoseconds. That's nice. It's scalable. We have to think about fridges and so on, but I'll try to argue that it's scalable. And you can even build more complex architectures around this kind of artificial atoms as I will make. So that's like a one-slide overview. Now let me just go a little bit slower. Yes.
You mentioned it before, and now you mentioned it again. You use this transmon, right? And it has many levels, right? So in principle, you use just the two first levels for computation, but like it could in principle jump to the next level.
Yes.
But this would be an error, right?
Yes.
And you're not considering this in your error correction mode, right?
Right.
And so what?
Great question. Yeah, very good question. Right. So the question is, as happens in atoms as well over here, right? So you have this unharmonic oscillator, right, which I'll explain the physics of it, but we use to encode our information. And I'll say the qubit is just the first two levels, right, 0 and 1. But there's all these other levels, right? And of course, there is like thermal excitation that can lead you to the second level, right, to level 2, or even further, right? Now, when I was talking about error correction, I talked everything in terms of it was a really a qubit there, right? So there was no extra levels there. So the question is that physical error that will take you from the one state to the two states is an error that is not described by just polymatrix X and Z, right? And that's very true. Okay, you're right. This is called leakage error, and it's very important in superconducting qubits. So in every error correction scheme, unfortunately, I won't explain the details of that, but you have to correct for them as well. So whenever you think about error correction for superconducting qubits, it's not just X and Z, it's a little bit more complicated. There's leakage errors as well. Luckily, these leakage errors, they are easy to correct, right? Because kind of, for example, you can just detect, that's a simplified way of doing that, but it kind of works. You can just detect in a non-destructive way if you are in the subspace of 2 or more excitations versus 0 and 1. And then if you are there, you say, oh, there's a leakage, okay, I just reset, right? And if you say, oh, there's no leakage, fine, I just continue, right? So because error correction is easier for leakage, is that it's okay to gloss over, but you're completely right, it's something that we have to correct for. All right, that was a good question. 10 minutes or how much time?
It doesn't end.
Okay. 8. All right. So yeah, I'll just start. So what are the components, right? So there's this qubit chip. These are all pictures from the lab at AWS and Amazon where we're doing these things. So the qubits, this is a channel, but I'll get to that later, right? There's like a control line, it's just a transmission line, you send microwave signals. Then there's like a big capacitor, usually there's like this funny shape in the capacitor, and there's like a tiny junction which is way smaller than the capacitor, and that's called the qubits. You imprint, right? So like a silicon wafer, and you have this kind of earthy aluminum here. Then you need to isolate this as much as you can from external noise. So you have to build a package around this. How to build the right package is like very crucial, right? And I don't understand anything about it, but we have people that do it very well. Then there is the cryogenics. And the cryogenics, we use this fridge that's, probably you've seen a picture, right? Because they look nice, so usually people like to show them. And the qubits sit here at the bottom, and they go by stages, right? So they're like temperature stages. So there's all these control lines, to control the qubits. They go down from kind of some, from some classical hardware that sits outside the fridge that sends the signal. And the chip sits here at the bottom. And the bottom is very cold, it's like 20 millikelvin, sometimes 15 millikelvin. So very cold, right, outside its room temperature. And then in stages, it gets cooled and cooled, right, and you attenuate the signals to handle everything. And this is one of our colleagues, right, just setting up the switch in the lab that we have at Caltech. So what is outside is a bunch of control electronics, right? So there's a lot of control electronics outside, which is used to convert, right, the signals from digital to analog, and then sent through this, coaxial cables to the chip, right, to the quantum chip at the bottom of the dilution refrigerator. So just another picture. This one is from Google, I think, right? So, but it's the same kind of fridge. Everyone buys from the same. It's like Ruforce, is a company in Finland, and they build the best fridges currently. And so this coax, or the coaxial cables, they send the microwave signals to the qubits. This is like the staggered temperature stages where it moves more and more. Right here is where you have your quantum chip with the package around this, right? And the idea is that really, right, we want to use superconductivity, and we will use these cryostats to preserve most of quantum behavior, right? To really filter as much as noise as possible, right? So it's kind of like a full stack development, right? To build a quantum computer out of this, that everyone has to work if you want to do it, that we do as well. So it starts, you have to have a quantum algorithm that you want to run, right? In terms of the circuit, for example. Then you need some control software, right? Which maps the circuit into kind of the analog signals that you send through. Then you need some control electronics, right? Which you just send the signal. Then this gets mapped into some microwave signal process to send the microwaves here down. Then of course you need the cryogenics, right, for cooling this down, and all the interconnects for basic attenuators and so on to make sure that there is no heating from these control lines that is destroying your cryogenic cooling. And finally you have the device at the bottom, right, really the quantum things that you wanna explore. So how much time?
6 minutes.
Okay, so I think, because what I want to start doing, but I'll start next time because it's a good beginning. It's just explaining more details to how the superconducting qubits work, right? So I think I'll just stop here. Thank you.
Further questions?
So hi, thanks for the lecture. And as you can see, for reaching practical quantum computation,
one of three things. You can get better qubits, better physical qubits, lowering their error rate. You can get more qubits, so you can make larger surface codes or other correction codes. Or you can get better error correction codes that requires less redundancy or something like that. So currently, like for the big players, Google, IBM, Amazon, China, and so on, what are their best hopes? They think they can increase in all those three aspects, or they think that, okay, we cannot get better physical qubits, so we have to increase the number of qubits, or something else. And what are your opinion on the matter?
So that's an interesting question. I think right now, maybe it has changed, but I think right now, all the big players, everyone in the community that works on this, I think knows that we have to improve on all three of them, right? Especially the first two. I think the first two is very clear, right? There will be better gates, so we have to make it very clear. Even if you just want to use surface code, because as I will show, it's not like sufficiently below the threshold right now, so that everyone knows. That we need larger codes also, there's no way, right? Because you need, but the question is really like a code of distance 21 or 15 or 31, but that's the question, right? And better codes, that's where it gets interesting. There is the hardware efficiency, which is a way of doing that. You're still using surface code, but you do something more clever at the physical level. There is something that we're doing at Amazon. There's some startups that work on that as well. Google and IBM, I don't know if they have been doing that yet, as far as I know. Microsoft, of course, the whole program is about getting better qubits, right, which is topological to do, although it has some hard to do. In terms of better codes, like going beyond the surface code, right, that's a very interesting direction. Companies are not doing that. There's people, they have constant people doing that. There's many big academic thinking about that. And the challenge there is that it might be the pays off at some point, but you need much better physical error rates. So the codes that we know, they might only be better than the surface code. If the physical error rates are kind of like 10 to the minus 4 level, right? And we're still far away from that. But there's definitely a lot of theory work being developed. And I think it is maybe the ultimate solution will be a different code than the surface code, but that will require better physical error rates.
Thank you.
Thank you for the lecture. When you are working with superconducting qubits, you have many resonators hooked to transmon, right? For example, when you calculate the Hamiltonian using the capacitance matrix, you find that you have many iterations beyond first neighbor qubits or first neighbor resonators. How do you control this iteration beyond first neighbor qubits? Because it can be dangerous, for example.
Right. So you talk about crosstalk, right? So the question is, suppose you have a square lattice, right, as in the surface code of some superconducting qubits. But even though the dominant interaction strength is near neighbor, right, there is some non-near neighbor interactions there, right? And even though you don't want to use that for the gates, because your gates are local, they become noise, right? So and that's very true. And there is like data showing that, right? So if you take some quantum shifts that people do on a large number of qubits, you get a distribution of errors, right, which has like 3-body, 4-body errors there. So usually what happens is that they are there, but their strength decreases, right, with the weights. So surface code also works in that case. You can still work. Just the threshold will change. Right? The threshold will change. The performance will change. So in this realistic error model, you also include crosstalk there, right? You also include these higher order error terms, and you see how they behave. And of course, if there is a very non-local error there, which has high probabilities, it will not work. But that's not the case, fortunately, right? So they do decrease the weights. So then, it still works in practice, and I will show experiments where it's kind of working, even though they have a lot of these higher order terms there.
Well, so I think we are almost on time. Let's continue like that and thank Fernando again for this.
I'll have some half announcements, so it's not complete. None of them is complete, but Fernando, you are the first to receive your cachaça bottles that we will sell soon, but not now. So this is part of the half announcement, and you see that there are the two models. the regular one, the gold one, and the other one, the gold one, and the Gabriela one. And the prices were already announced yesterday, and we'll probably start selling this afternoon or during lunchtime, something like this. I also have to update our announcement about the boat trip. As you have seen, and it's quite usual here in Paraty, weather changes very fast, and we try to adapt and to optimize, error correct, and whatever. So we'll probably change the schedules of the Wednesday and Thursday. So whoever has to show a poster on Thursday, you have 24 hours less. You probably will have 24 hours less, so please keep your posters ready for this change that will be very good, including for you. Because instead of not going to the boat in order to have your poster finish it, you have to finish it somehow until tomorrow and go to the boat trip after, whatever. Okay?
But the poster session is going to be tomorrow.
If we confirm the change, we'll change the complete schedule.
Okay.
So everything that is foreseen for Wednesday will be on Thursday, and things from Thursday on Wednesday, including poster session. Okay? Any other announcement? And
all slides are online, including mine.
great. The website already have a new part called slides. I'm not sure if in the last minutes the slides appear there, but
Not just the slides are there.
not just the slides are
It's
there.
not empty.
And Richard's also, I believe. So we can say that half of the slides are there, and soon we'll be as close as possible to 100% and no errors on this. Okay? For you not to be Markovian and to realize that there is memory in the system. Okay.
So we reunite here in, let's say, 25 minutes. So 5 minutes, that's for the coffee.